when searching for residential electrical plans in CAD.dwg format. There are several avenues you can explore, both for free and paid options. For free plans, resources such as Autodesk Snap-EDA offer residential electrical plans specifically for single-family homes. Other websites like CAD.dwg provide electrical plans suitable for small houses or even two-story houses. Electricalplan.com also offers sample electrical plans for single-family houses. For those willing to invest in paid plans, CAD Blocks Free.com provides residential electrical design CAD blocks. CAD Library.net has a category dedicated to electrical plans. Home Designer and ArcHline XP offer residential electrical plans as part of their software packages. When selecting a CAD plan, there are several key considerations. Firstly, ensure that the plan is indeed in DWG format, which is compatible with most CAD software. Secondly, carefully check the scale and dimensions of the plan to make sure it accurately fits the specific requirements of the project. Thirdly, prioritize plans that include a detailed panel layout showing circuit breaker information. Fourthly, look for plans that offer multiple options for panel placement and various wiring configurations. When it comes to residential electrical service requirements, the National Electrical Code or NEC specifies minimum requirements to ensure safety and proper functioning of the electrical system. These requirements can vary based on the size and type of dwelling. For example, according to NEC section 220.82, the standard calculation method for a dwelling unit involves calculating the general lighting load at 3 volt amps per square foot. This calculation is detailed in NEC table 220.12. To determine the service size, first calculate the general lighting load. Secondly, add the small appliance circuits and laundry circuits, each rated at 1500 volt amps, as per NEC section 220.52. Thirdly, include the fixed appliance loads such as dishwashers, disposals, and water heaters, using their nameplate ratings. Fourthly, factor in the heating and air conditioning loads, selecting the larger of the two. Fifthly, apply a demand factor to the total load, as allowed by NEC section 220.82, to account for non-coincident loads. The resulting value determines the minimum service size required, typically expressed in amps of the service voltage, like 100 amps, 200 amps, or higher depending on the total calculated load. For a small house, a 100 amp service might suffice, while larger homes with more appliances and electrical demands may require a 200 amp or even larger service. Regarding panel layout considerations, the NEC provides guidelines for the physical installation and arrangement of circuit breakers within the panel. NEC section 408.36 specifies requirement for the overcurrent protection of panel boards. NEC section 408.38 covers the minimum spacing between busbars and components within the panel to prevent arcing. When designing the panel layout, it's important to group circuits logically. Firstly, dedicate separate circuits for lighting, general receptacles, and small appliance circuits. Secondly, assign individual circuits to major appliances like refrigerators, ovens, and air conditioners. Thirdly, use dedicated circuits for sensitive electronic equipment to minimize interference. Fourthly, label each circuit breaker clearly with its corresponding load for easy identification. Consider using a combination of single-pole and double-pole breakers depending on the voltage requirements of the loads. For example, 120-volt circuits use single-pole breakers, while 240-volt circuits, such as those for electric ranges and dryers, use double-pole breakers. In terms of wiring configurations, the NEC specifies various wiring methods suitable for residential applications. Common wiring methods include non-metallic sheath cable, also known as Romex, electrical metallic tubing or EMT, and rigid metal conduit or RMC. Non-metallic sheath cable is commonly used for interior wiring, while EMT and RMC are often used for exposed locations or underground installations. When running wires, follow the NEC guidelines for ampacity, which is the maximum current a conductor can carry safely. NEC Table 310.15b16 provides ampacity ratings for various conductor sizes and insulation types. Ensure that the wire size is appropriate for the circuit breaker size and the load it will serve. For example, a 15 amp circuit typically uses number 14 American wire gauge or AWG wire, while a 20 amp circuit typically uses number 12 AWG wire. When making connections, use approved wiring devices and techniques. Firstly, ensure that all connections are tight and secure to prevent loose connections and arcing. Secondly, use wire connectors or terminals that are listed for the specific wire size and type. Thirdly, ground all metallic enclosures and equipment to provide a safe path for fault current. Fourthly, follow the NEC guidelines for grounding and bonding to minimize the risk of electric shock. Remember that electrical work can be dangerous, so it is advisable to consult with a qualified electrician or electrical engineer to ensure that the electrical plan complies with all applicable codes and standards. When reviewing a CAD plan for a residential electrical system, several factors need to be assessed to ensure it meets safety standards, functional requirements, and local codes. Firstly, verify the accuracy and completeness of the plan. Check that all electrical components such as outlets, switches, lighting fixtures, and appliances are clearly indicated and properly located on the plan. Secondly, examine the panel layout. Ensure that the plan includes a detailed panel schedule showing the size and type of each circuit breaker, as well as the load served by each circuit. Thirdly, review the wiring diagram. Make sure that the plan includes a clear and concise wiring diagram showing the connections between all electrical components. Fourthly, confirm the compliance with the National Electrical Code, also known as NEC. Check that the plan complies with all applicable requirements of the NEC, including those related to wiring methods, overcurrent protection, grounding, and bonding. Fifthly, evaluate the load calculations. Verify that the plan includes accurate load calculations to determine the size of the service entrance, feeders, and branch circuits. Sixthly, assess the grounding and bonding system. Ensure that the plan includes a properly designed grounding and bonding system to minimize the risk of electric shock. Seventhly, consider the placement of outlets and switches. Check that the plan includes an adequate number of outlets and switches located in convenient locations throughout the house. Eighthly, evaluate the lighting design. Make sure that the plan includes a well-designed lighting system that provides adequate illumination for all areas of the house. Ninthly, review the appliance circuits. Confirm that the plan includes dedicated circuits for major appliances such as refrigerators, ovens, and air conditioners. Tenthly, assess the special systems. Check that the plan includes provisions for special systems such as smoke detectors, carbon monoxide detectors, and security systems. Consider the potential for future expansion. Ensure that the plan includes adequate capacity for future electrical needs, such as additional circuits for new appliances or equipment. Also, verify the local code compliance. Check that the plan complies with all applicable local codes and regulations, which may be more stringent than the NEC. Consider the energy efficiency. Evaluate the plan for opportunities to improve energy efficiency, such as using energy-efficient lighting fixtures and appliances. Assess the safety features. Make sure that the plan includes adequate safety features, such as ground fault circuit interrupters, also known as GFCIs, in wet locations. And lastly, consult with a qualified electrician or electrical engineer. Seek the advice of a qualified electrician or electrical engineer to review the plan and ensure that it meets all applicable requirements. Ground fault circuit interrupters are crucial safety devices designed to protect individuals from electrical shock. According to NEC Section 210.8, GFCI protection is required in various locations within a dwelling unit where there is a higher risk of exposure to moisture or water. One such location is bathrooms. NEC Section 210.8a mandates GFCI protection for all 125 volt, 15 amp and 20 amp receptacles installed in bathrooms. This includes receptacles located near sinks, tubs, and showers. Kitchens also require GFCI protection. NEC section 210.86 specifies that all 125 volt, 15 amp and 20 amp receptacles serving countertop surfaces in kitchens must be GFCI protected. This is because countertops are often exposed to water and spills, increasing the risk of electric shock. Outdoor areas are another critical location for GFCI protection. NEC section 210.8A3 requires GFCI protection for all 125 volt, 15 amp and 20 amp receptacles installed outdoors. This includes receptacles located on decks, patios, balconies, and in gardens. Unfinished basements are also subject to GFCI requirements. NEC section 210.85 mandates GFCI protection for all 125 volt, 15 amp and 20 amp receptacles installed in unfinished basements. This is because unfinished basements are often damp and have concrete floors, which can increase the risk of electric shock. Garages also require GFCI protection. NEC section 210.8 ATWA specifies that all 125 volt, 15 amp and 20 amp receptacles installed in garages must be GFCI protected. This is because garages are often used for working with power tools and equipment, which can increase the risk of electric shock. In addition to these specific locations, NEC section 210.8b requires GFCI protection for other locations where there is a foreseeable risk of electric shock. This includes areas near swimming pools, hot tubs, and spas, as well as locations where electrical equipment is likely to come into contact with water. When installing GFCI protection, it is important to follow the manufacturer's instructions and the requirements of the NEC. GFCI receptacles and circuit breakers are designed to detect ground faults, which occur when electricity flows through an unintended path, such as a person's body. When a ground fault is detected, the GFCI device quickly interrupts the flow of electricity, preventing electric shock. There are two main types of GFCI devices. GFCI receptacles are installed in place of standard receptacles and provide GFCI protection at the point of use. GFCI circuit breakers are installed in the electrical panel and provide GFCI protection for the entire circuit. When selecting a GFCI device, it is important to choose one that is listed by a recognized testing laboratory, such as Underwriters Laboratories, also known as UL. Listed GFCI devices have been tested and certified to meet safety standards. Regular testing of GFCI devices is also essential to ensure that they are functioning properly. GFCI receptacles and circuit breakers typically have a test button that can be used to verify their operation. It is recommended to test GFCI devices monthly to ensure that they are providing adequate protection. Also, it is good practice to use arc fault circuit interrupters, also known as FSIs. Arc fault circuit interrupters are devices designed to protect against fires caused by arcing faults in electrical wiring. According to NEC section 210.12, FSI protection is required in various locations within a dwelling unit, particularly in branch circuits that supply power to bedrooms, living rooms, dining rooms, family rooms, recreation rooms, and similar areas. FSI devices are designed to detect arc faults, which are dangerous electrical conditions that can occur when there is a break or weakening in the insulation of electrical wiring. Arc faults can generate excessive heat and sparks, which can ignite nearby combustible materials and cause a fire. FSI devices work by continuously monitoring the electrical current flowing through the circuit. When an arc fault is detected, the FSI device quickly interrupts the flow of electricity, preventing the arc fault from escalating into a fire. There are two main types of FSI devices. FSI circuit breakers are installed in the electrical panel and provide FSI protection for the entire circuit. FSI receptacles are installed in place of standard receptacles and provide FSI protection at the point of use. When selecting an FSI device, it is important to choose one that is listed by a recognized testing laboratory, such as UL. Listed FSI devices have been tested and certified to meet safety standards. Regular testing of FSI devices is also essential to ensure that they are functioning properly. FSI circuit breakers typically have a test button that can be used to verify their operation. It is recommended to test SI devices monthly to ensure that they are providing adequate protection. When planning the electrical system for a residential building, it is crucial to consider the potential for future expansion and changes in electrical needs. This can be achieved by incorporating several design strategies to accommodate future electrical demands. Firstly, provide spare capacity in the electrical panel. Install an electrical panel with more circuit breaker slots than are initially needed. This allows for the addition of new circuits in the future without having to replace the entire panel. Secondly, run extra conduit to strategic locations. Install empty conduits, which are pipes used to protect electrical wiring, to areas where future electrical needs are anticipated. This makes it easier to add new wiring in the future without having to tear into walls or ceilings. Thirdly, use appropriately sized wiring. Install wiring with a higher ampacity rating than is currently required. This allows for the addition of higher wattage appliances or equipment in the future without having to replace the wiring. Fourthly, install additional outlets and switches. Provide extra outlets and switches in areas where they may be needed in the future, such as home offices, workshops, or entertainment rooms. Fifthly, consider smart home technologies. Incorporate smart home technologies such as smart lighting, smart thermostats, and smart appliances which can be easily upgraded or expanded in the future. Sixthly, plan for electric vehicle charging. If there is a possibility of owning an electric vehicle in the future, plan for the installation of an electric vehicle charging station in the garage or driveway. Seventhly, provide dedicated circuits for specific appliances. Install dedicated circuits for high wattage appliances such as refrigerators, ovens, and air conditioners to prevent overloading of circuits. Eighthly, consider the location of the electrical panel. Locate the electrical panel in an easily accessible location where it can be easily serviced or upgraded in the future. Ninthly, use flexible wiring methods. Use flexible wiring methods such as flexible metal conduit or armored cable to make it easier to add or modify wiring in the future. Tenthly, consult with a qualified electrician or electrical engineer. Seek the advice of a qualified electrician or electrical engineer to design an electrical system that meets current needs and can accommodate future changes. By incorporating these design strategies, homeowners can ensure that their electrical system is capable of meeting their future needs and providing a safe and reliable source of power. Remember that electrical codes and standards are subject to change over time. It is important to stay up to date with the latest requirements to ensure that the electrical system is always in compliance. Also, electrical work can be dangerous, so it is advisable to hire a qualified electrician to perform any electrical work. The electrician will be familiar with the latest codes and standards and will have the necessary skills and experience to perform the work safely and correctly.